Today we study Faraday's law. Faraday's law of induction is related to the changing magnetic field passing through a circuit. There's a loop and magnetic field is coming in. This is external magnetic field, and we define the flux, magnetic flux phi b by the integral of magnetic field. So we make a scalar product with the differential area over the surface. This is surface. Sure, dA should be normal. Direction of the dA normal is normal to the surface, and if we follow the boundary of the surface, the direction of the normal vector is following the this will counterclockwise, then the normal direction of the area is this direction. It is related to magnetic flux. If the magnetic flux on the surface changes depending on time, then there's a EMF is generated. Before we go ahead, we consider the SI unit of magnetic flux. Magnetic flux is Weber, written by Weber. We can write WB. And here, capital T is Tesla, that represent the B field dimensions, the unit of the B field. The magnetic field multiplied by area. So the Weber is the SI unit of the magnetic flux. Faraday's law of induction is related to the changing magnetic flux. The magnetic field is passing through a surface. Then we integrate this amount to find out the magnetic flux, and if this flux changes with respect to time, we have the EMF proportional to the change in time as a time derivative, and there is a direction opposite to avoid the change. So when we have a circuit, something like that, if you make a complete loop, when you return the same position, the potential is independent of time. I mean the potential when you return the same position, then V is fixed. So delta V over a loop must be 0. However, if there is a change in flux passing through a circuit, delta V is non-zero, and delta V is non-zero. That is the induced EMF. This induced EMF is something like a battery. It is not a physical battery, but it is due to the field, change of field. We have a surface, but if you make a one loop and two loop, then although the area is the same, the number of turns, one turn, two turns, three turns, and four turns, number of turns increase the magnitude of the flux. This phi b is for single loop and n loop. Therefore, if you make a turn, induced EMF is magnified by a factor of turn, number of turns. Lenz's law is the law related to negative side. For example, North Pole is approaching a circuit. When North Pole is approaching, North Pole is generated. So north to north, they repel. So this negative sign is called the Lenz's law, and the direction of the induced current is to oppose the change of the magnetic flux. For example, on the other hand, if North Pole is away, then it makes South Pole is generated. North Pole is going away, it becomes weaker. So the flux, it becomes weaker. So this South Pole is generated to hold this North Pole, not to move away. Okay, that in order to make the South Pole on the left, the induced current should be generated along this direction. That is opposite to the left-hand case. When you close the switch, the current flows, and here this part, current comes in, I, and magnetic field is generated. E field is generated. And there is another coil, and there is a galvanometer. That is a very sensitive ammeter, Ampere meter. When the magnetic field comes in, it just like North Pole is approaching. If North Pole is approaching, it wants to make a North Pole. North Pole is approaching, so it opposes. So in order to make a North Pole, then current is flowing its direction. When you turn off magnetic field, when you turn off the switch, the magnetic field disappears. That means your North Pole is going away. In order to oppose this motion, you have to generate the South Pole in here. In order to make a South Pole, magnetic field must go down, and this induced current is this direction. This direction. That is opposite to the previous case. A rectangular loop of area A is placed perpendicular to the uniform magnetic field. So magnetic field is uniform. And the loop is spun around one of its sides. So this is a center, and if you look at this one in here, then this is a loop, and magnetic field is coming out. And there's an axis, and this loop is rotating. The normal direction of the loop is in this direction. And the magnetic field is along the x-axis. We have a y-axis. We have n direction. This is n. So magnetic flux phi b is b dot dA, and E equals to bi dot area is a fixed area, and I cosine omega t plus phi plus j something. But this j component does not contribute because I dot j equals 0 and I dot I equals 1. Hence we have BA cosine omega t plus phi. The time derivative is time derivative of minus omega sine. So minus omega BA sine omega t plus phi, but there is additional negative sign due to the Lenz's law. We have positive sign. That is the amount of EMF, induced EMF. And the direction, this is N, the direction is this. Induction and energy transfer. We consider the energy transfer in induction. Force to change magnetic flux. There's a loop. There's a loop, and B field is going into the page. And if you pull this circuit to the right, then the induced magnetic field is generated to hold this one, to keep this magnetic field flux unchanged. So if you move this one, it is something like we have a circuit is moving, and it is something like your magnetic field is coming in, but the amount of magnetic field flux is changing. That means the north pole is moving away. That means you have to generate the south pole in here. In order to make a south pole, you have to make induced current along clockwise direction. So this is induced current is along this direction. If you have an induced current here, F1, you have F1. Current is going up. Magnetic field is, this is the paper. Magnetic field is coming in. Magnetic force, F is Q V cross B, or I L cross V. So current direction, magnetic field direction. So this is the magnetic force. So magnetic force F1 is toward this direction. Therefore, if you want to keep the velocity the same, that means you have to make an equilibrium with the force F1. Minus F1 is applied by your mechanical force. Your force. You apply this force, and this force cancels this. What about the upper and lower part of the circuit? This upper part of the circuit, upper part, current I is flowing, magnetic field is coming in, so this magnetic field is better to write the magnetic field in this way, or current I, and magnetic field is here, and F2 is upward. So yes, F2 is upward. And here, current is flowing left, so current is in opposite direction. Thus, the force F3 is opposite. Because everything is the same except for the current direction, this F2 and F2 cancels. So there is no force applied to the loop due to this upper and lower wire. So the only force, net magnetic force is F1. And in order to keep the velocity the same, what you have to do is you apply the same amount but along the opposite direction applied to the wire. And detailed calculations are given here. And power, of course, F times V. And that F must be by making use of magnetic field and length L and ILB. This is the magnetic force on this F1. Times velocity. Force times velocity is the power. The force is on the left, to the left, and V is to the right. So this power is negative. Your external force is, the V is the same, but your external force is to the right. So power induced. Induced current's power is negative, and the power of your external force minus FB positive. Sum of two power is 0. That's the reason why this whole amount is moving with the same velocity. The kinetic energy is invariant. Suppose that there is a resistor. Then current I flows, and the power, the lost power, due to the current is I squared R. And we have potential difference E equals IR. So I times E, and this E is EMF. EMF can be obtained by I times VLV. This EMF determines the current relationship between the current and velocity. Sure. The L is the width and R is the resistance. Hence the force is ILB, and we substitute I in here. We have B squared L squared V over R. The power of mechanical work is then this amount. Eddy current. Induced electric field can be created in a massive object as well as in a circuit. Circuit has a specific path, either this direction or that direction. But in case we have metal plate, or some volume of matter, if the magnetic field flux changes, then the induced electric field is generated and the current can be created inside this plate or some volume. So because of the induced, this is called the eddy current. We encounter an opposing force that must do work, and the same thing, the same as the circuit. The electromagnetic braking system in a high-speed train is an application of eddy current. Induction range is also an application of eddy current. Each time the plate enters and leaves the field, the portion of its mechanical energy is transferred to its thermal energy because there is some resistivity in this material. If the matter is in a completely superconducting phase, then once you change the magnetic field, induced electric field is generated and current is produced, and then that current is flowing forever. Next, we consider induced electric field. Induced electric field, consider copper ring. This is a conductor. This is a conductor. A lump of conductor. And we draw ring C inside a conductor. And let us consider the magnetic field flux passing through the imaginary circular circuit. Changing magnetic field produces an induced electric field. Suppose that this B field is entering, so B field is entering. If B increases, so north pole is approaching, then we have to produce a north pole. In order to make a north pole, our induced current must be produced along this direction. The changing magnetic field produces an induced electric field. The EMF of the induced electric field around the circuit C is this. So this is induced current. Induced current is generated because of this EMF, induced EMF. The work W done on a charge Q0 during a single revolution of a long circuit C by the induced electric field, work, force, displacement along a loop. Force is Q times E. This is induced electric field. and Q0 is factored out, charge is invariant, so integration over the electric field, this one is the EMF. And according to the Faraday's law, this EMF is minus magnetic flux passing through the surface this circuit is the boundary of this surface. New look at electric potential. A field line of induced electric fields form a closed loop. Electric field forms a closed loop. If you follow this curve, integrate along the path, or close the path, then you will get the EMF. And that EMF is minus d phi. Okay? If there is no change in the magnetic flux, this is true. And this is for the electrostatic potential. That's the reason why we wrote static. Static is time independent. So this is time dependent. Time dependent. Static, time independent. If the magnetic field is independent of time, then along the closed loop, electric field integral must be 0. However, if the magnetic field is depending on time, it is non-zero. And actually, this one is related to the case, the conservative force field. Force is a minus a gradient of potential energy. Using this electric field is a minus the gradient of potential. In that case, ds equals 0, because this is a total differential. Gradient v dx equals this is dz. This is total differential. Therefore, if you make integral over closed path, then you end up with x1 v minus x1, the same point. It must be 0. But that is true only for the electrostatic case. There is no time dependence. Actually, the magnetic field contribution comes in an additional term that is not written in here. Inductors and inductance. A circuit itself generates a magnetic field if there is a current I is flowing. So magnetic flux is B times dA on the surface. If there is this circuit is wound by n turns, then we have additional vector n. And this one is always proportional to current. Therefore, N phi B is something multiplied by current. And we call this something, this constant, as inductance. The unit of inductance is Henry. Or you can just simply write capital H. Inductance is the flux divided by current, so flux, magnetic field times the area divided by current. So, Faraday's law is this, and substitute the inductance formula in here. So, Faraday's law in terms of inductance is written in this form. This formula is quite useful for circuit analysis. We can consider a solenoid of n windings. Here L is the length and small n is the number of windings per unit length. We assume that there is an internal magnetic field is V and cross-sectional area is A. We have A, solenoids, and number of turns, and the length is L, and current I is flowing. Ampere's law can be used because the magnetic field is only inside, and outside we assume the magnetic field is vanishing. B dot dl, our closed path is just BL. And Amperian loop is this one. We have current each I, and there are n turns, and mu 0 I enclosed is capital Ni. Therefore, magnetic field is like that. The number of terms is n, flux phi b, that should be, by definition, Li. And flux is area times magnetic field. That's mu 0 and I. So we have factor II, they cancel. Therefore, L is mu 0 small n capital N A, and capital N is mu 0 and capital N is N L A. So mu 0 n squared AL, this is the volume. A times L. Therefore, this is a small n squared. Or we can substitute n equals capital N over L. So the L cancels. So capital N squared cross-sectional area divided by L. Self-induction. This is RL circuit. RL circuit. So consider a circuit consisting of a solenoid of inductance L and a resistor whose resistance R changes. As R varies, the current I of the circuit also varies. Follow with me. Because this EMF is fixed, if R varies as a function of time, the current I changes. If the current I is proportional to the flux, and the flux changes because of the changing resistance. When flux changes, because N phi B is Li, the current changes. There's an induced electric field is generated to oppose the change of current. Anyway, if the current is fixed, independent of time, then there is no EMF, induced EMF, in the coil. Suppose that we have L inductors connected in series. Then L1, L2, Ln. Because if they are connected in series, current I is common. The potential difference is minus L1, and if we add everything together until Ln di over dt, then we can combine everything all together. So the net EMF, induced EMF, is a sum of E1, E2, and En. So EMF is the sum because they are connected in series. And if we substitute this one in here, negative sign over negative sign, inductances are summed over, and we have a common time derivative of current. Hence, this overall factor that is the sum of the inductances is the equivalent inductance of the whole system. If n inductors are connected in parallel, the EMF of the whole system is this. And there is a current I1, I2, until IN. Current is distributed. So total current is I, and they are sum of all partial currents. And EMF is identical to any case. So E equals E1 through En. So this is the same for everything. The whole system has an equivalent inductance multiplied by time derivative of total current. And this EMF is the same for everything. So this is minus L1 time derivative of I1 until minus Ln inductance of the nth inductor time derivative of In's. So if we divide this minus inductance, then current IK time derivative is EMF divided by minus LK. The total current is the sum of partial currents. And if we take the time derivative of total current is the sum of time derivative of partial currents. And we substitute this one in here. Then we end up with the left hand side is this one is E over minus L, and this one is E over L1 minus E over L2 and minus E over Ln. If we divide common factor E out, then we end up with L equivalent. Reciprocal of N equivalent is the sum of reciprocal of the inductances. That is the case for the N inductors connected in parallel. RL circuit. We have resistor, inductor, and external EMF. When we switch on, then the current flows in. So current flows in, so we have L di over dt. Induced EMF is generated in here to oppose the change. So if we keep the current keeps on flowing, at some point it reaches the point, it is something like there is a steady current is achieved, then this guy minus I is constant, then this one disappears and it looks like just simple R. So the importance of this inductance appears when it switches on or off. So the derivative of current is the most important parameter that determines the potential difference between the two terminals of an inductor. A. As soon as the switch is closed at t equals 0, the current suddenly rises. So Inductor wants to oppose this change in current. The self-inductance opposes this change of current. Crossing the battery along I, the potential shifts by plus C. Crossing R, potential decreases by IR minus IR. Crossing L along I, the potential decreases by minus L, this amount. So loop rule shows this increased, decreased, decrease. So this is the equation for this circuit equation for our L circuit. The particular solution can be obtained in an easy way. Particular solution I equals constant, then di over dt equals 0 is a particular solution. So if we substitute particular solution, R L I P equals E. Therefore, L is divided in both sides, so there should be L in the denominator. So LL cancels, and IP, particular solution, is E over R. That's written in here. The general solution of this equation is the particular solution plus the solution for the homogeneous equation. And this homogeneous equation can be integrated. So IN log IN plus constant. So I homogeneous. I homogeneous T equals alpha T. Right? So particular solution is this one. Alpha E minus alpha L T. The time scale, this is L. L. So this can be written E over R plus alpha E over T over tau. Tau equals L over R. This is time constant. This constant alpha is determined depending on the initial condition. Alpha is written in C here. If I equals 0 at t equals 0, so that means equals 0, C equals minus E over R. Therefore, if we substitute in this result, the final result is like that. This one is for I 0 equal 0 case. In the limit t goes to infinity, this one goes to 0. So as t goes to infinity, current I becomes constant. This means E R I is constant. That means time derivative current is 0. So there is no VL becomes 0. So it's the same as the single R circuit. As we have already discussed, this is the time constant. And if we substitute explicit numerical value, then you will find about 63% of the amount of current is saturated when T equals tau. It's L over R. You must be familiar with the units. Henry is for the inductance. Ohm is for the resistance. And the answer is Henry over ohm is 1 second. Current decay. If the switch is closed on A and long enough, then we reach I becomes E over R. So suppose that we have I0 is E over R, and suddenly put this switch on B. Then there is no battery. Then equation becomes a homogeneous equation because E is vanishing. This one is missing. The answer is this homogeneous equation has the solution to this. However, we have a constraint I0 equals E over R. Therefore, that means C equals E over R. Therefore, IT is E over R multiplied by the exponential. Again, time constant tau is L over R. Okay, let us consider a linear equation. A is a square matrix. X is a column vector that are unknown. B is a column vector, known values. Multiplication of two matrices, A, B, C, D. Multiplication is made in row multiplied by column. Row multiplied by column, xy. This is ax plus by. In such a manner, a, b, this part is ab zw. Az plus bw. cd cdxy cx dy cd zw cz plus the dw. So this is the first 1 1 1 2 2 1 is this 2 2. So 1 1 1 2 2 1 2 2 elements are computed in this way. A has an inverse when it's a determinant. Determinant of A is AD minus BC. If determinant is non-zero, inverse is 1 over determinant and flipped and put negative sign on it. This is the inverse. Inverse is multiplied to the right or to the left. In either case, it must produce identity matrix. If there is an inverse, if the determinant of A is non-zero, then this linear equation is solved by Ax equals B. We multiply A inverse and this is identity. Identity matrix is multiplied. Identity matrix is multiplied to any matrix. This is the same. So this is X. X equals A inverse B. A inverse 1 over AD minus BC and DA minus B minus C. This is PQ. This is written here. Multiply this one, dP minus BQ minus CP AQ. Okay, this is the solution for this linear equation when A has non-vanishing determinant. Using this one, you can solve the various problems. First, you have some circuit, then you find the loop, this or this. So there are three kinds of loops, but you can choose either two of them. Not all of the three loops are independent, because sum of two linear combination of two loops can produce the other loop. So anyway, you write down the equations. For example, I1, I2 for the current flowing R1, L, I1, and R2, something like that. So let the current flow in this direction. Then at this branch and this vertex, current conservation is used. In this loop, V is increased, minus IR, potential decreases, and minus I2R2, potential decreases. And this small loop, current flows in this direction, then minus I2R2, and in this direction, minus L di1 dt, right? So we have positive sign. First, we have these two equations to construct a linear equation. I1 plus I2, I, and R1, because this I equals I1 plus I2, so we have R1, I1 coming from this, and by expanding this, R1, R2 sum is multiplied to I2. The right hand side is B0. Now we can solve this equation for I1 and I2, and this expression becomes solvable. These are all known, and this is unknown. I is unknown. However, we can express I1 and I2 in terms of a single current. Inverse of this matrix is known. If you multiply the inverse based on this is the inverse, determinant is R1 minus R1 plus R2. So that is minus R2 is the determinant. 1 over determinant, flip the position and flip the sign. Okay? So I1, I2 is obtained by multiplying V0I to this inverse matrix. The result is this. And then you substitute this I1 and I2 in terms of I and the middle equation. This equation reduced to an equation for RC circuit, L circuit. We know the solution for this L circuit. Finally, we find the solution for this, and then once I is determined, then I1 and I2 are automatically determined through this. The next steps are straightforward. I don't describe in detail further. Energy stored in a magnetic field. There's a EMF R and L. The circuit equation for this RF circuit is in general of this form. We multiply current I. Then the left hand side is potential multiplied by current I. That means this is power supply. Supplied power. Power supplied by battery. that power must be the same as this one. This is a 1/2 Li squares derivative. So input power is a sum of two. Ri squared, this is Ri times I. This is VR times I. So power spent by R. And another energy, this is power saved in inductor. So 1/2 Li squared is called magnetic energy. We remember the magnetic energy can be expressed in terms of inductance. Substitute inductance of the solenoid, substitute in here. But we remember the magnetic field inside the inductor is mu0 and I. By making use of this one, UB, capital UB, divided by volume. Volume is the cross-sectional area multiplied by the length. This is the length of the solenoid, cross-section of the solenoid. This is volume, UB. So this is a small UB. The energy, magnetic energy density. If you simplify that expression, you end up with this. This is B squared over 2 mu0. You remember electric field energy density, that is 1/2 epsilon 0 E squared. This electrostatic field energy is saved inside a parallel capacitor, and this is the magnetic field energy density saved inside the solenoid. So electric field energy and magnetic field energy, the sum of them are conserved, but this is a source and this is sink and this is container for magnetic field energy, and this is a container for containing the electric field energy. Alright, so this is the energy density of the electric field and magnetic field. If you sum them, you'll find, because the product of permittivity and permeability is 1/2 speed of light squared, the electromagnetic energy density sum is 1/2 epsilon 0 permeability constant multiplied by the sum of electric field squared plus speed of light multiplied by magnetic field squared. We can follow this note to study mutual induction between two solenoids, disconnected solenoid in a different circuit. If you generate a magnetic field, it opposes the magnetic field too, so there's a induced electromagnetic EMF is generated. So disconnected circuits generates induced EMF, then we say the mutual induction. And we use a special symbol for the mutual inductance. Finally, Faraday's law is written in the form, and magnetic field flux is the sum of magnetic flux element, and we used Stokes' theorem to rewrite this line integral into surface integral as a curve. Now this surface, this isn't wrong, it's just a surface integral. And if we make use of this expression and this expression, substitute them into original Faraday's law, and move vector this sigma, the area element, and then shrink this surface into small tiny point, you'll find this integrand must disappear. And actually, this Faraday's law integral form of Faraday's law is written in the differential form of the Faraday's law. We are almost there. We have charge density over epsilon 0. Divergence of magnetic field vanishes because there is no magnetic monopole